Um, and Jaemin he had previous background on humanoids, in particular something called whole body control, who mentioned today several times, and is a type of control that deals with mostly sort of trajectory tracking for kind of complex robotic systems. And then since then, he's taken the whole body control to all sorts of directions. Normally very computationally expensive, and a lot of his work has been on finding strategies to formulate the problems into something very tractable, either for trajectory generation and to try to approach to make it feasible in sort of practical terms for computation, and or trajectory optimization, meaning that you're modifying motion planning trajectories into a way that they are realizable in these kind of complex robotic systems. Trajectory tracking as well, in a form of a feedback loop, and most recently stochastic formulations of these kind of optimization controllers. So he's one of my students, most theoretical, but also he has nice experimentation contributions as well. So I think that's all for my intro, and I'm gonna give the attention to Jaemin. Any question before we start? Any logistics, presentation, question by the audience, and then question by the faculty, and then we'll meet the faculty for deciding where to go. But any question? All right, Jaemin, fire it off.
Okay, thank you, Dr. Santis. Can you see my screen?
Yep.
Okay. Good morning, everyone. Thanks for joining this presentation. My name is Jaemin, and my supervisor is Dr. Santis, and co-supervisor is Dr. Bakulas. I'm here to present today to present my studies while pursuing a PhD. The title is Whole Body Trajectory Generation and Control Strategy for Multi-Contact Robots. This presentation will cover these chapters in my thesis, but I will briefly introduce some part of this thesis due to the time limitation. To begin, I will share with you some background and motivation of my studies. First, I'd like to introduce many robots I have experienced. In our lab, many robots have been developed and used. For example, Mercury, Draco 2, Scorpio, Dreamer, and Valkyrie. I believe these robots have distinguishable features. First, they generate human-like motion, such as dynamic locomotion and dexterous manipulation. Sometimes the robot produces legged manipulation like a human with a multi-contact. Secondly, we aim to put this robot in unstructured environment, such as real human life, because these robots give us really good productivity while doing assigned mission in that environment. Of course, the behavior should be optimal, in my opinion. Third, we should consider physical interaction, such as ground direction force or unknown disturbances. Lastly, human-centered robots are usually operated with a human-robot teaming, so they require safety-warranted behavior. Oops. Oh, sorry, something wrong here. Oh, trajectory generation and path planning have been broadly investigated in robotics community. To make continuous and smooth trajectory, we use many interpolation methods such as cubic spline and B-spline. Also, we have used RIT and PRM technique, which are basically based on sampling-based technique. However, we use this method for very simple cases, as you can see in this slide. Most examples are very simple, and they consider only some geometric or kinematic constraint. Of course, there are some researches considering complex robotic system, as shown in the last example. But they rely on the reduced order model, such as linear inverted pendulum model. But in reality, control process based on the full body dynamic model. So there is a discrepancy between the models in planning and control steps. This is one of critical issues in humanoid robot studies. In fact, contact is the main reason to make trajectory generation problems more difficult. Many complex robots like legged robot, manipulators, and humanoid robot involve multiple contacts and frequently change the contact sequence. Also, the contact-related constraints are typically mixed-state input nonlinear constraint. So we solve large-scale nonlinear optimal control problems to generate trajectories using optimal control techniques. According to recent publications, many research groups are utilizing nonlinear programming, mixed integer programming, and differential dynamic programming. As you know, it takes a really tremendous time to solve the largest scale nonlinear optimal control problem, especially like a humanoid robot. To speed up the computation time, we use many approximations and simplification methods. Also, we can use simplified models such as centroidal dynamics or linear inverted pendulum model to reduce the dimension of our system. However, the solution to this problem may not fulfill the full body constraint, such as joint position, velocity, torque constraint. Therefore, it is really important to solve the original nonlinear optimal control problem in a computationally efficient way. Let's move to the whole body control. Whole body control aims to define a small set of low-dimensional and straightforward rules, such as equilibrium, self-collision avoidance, and so on. So whole body control method warranted the exact execution of one or multiple tasks. In most cases, the multiple tasks have a hierarchy in terms of their importance. Also, whole body control will exploit the full capacity of the entire body in compliant multi-contact interaction with the environment. You can see many full body humanoid robots in the world. The whole body control will cover a lot of topics to control these robots. Whole body position force control, model-based dynamics control, centroidal moment control, multi-contact force distribution, agile locomotion, and dexterous manipulations. Here is motivation of my research. I'd like to introduce three main challenges for humanoid robot studies: trajectory generation, optimization, and tracking. My study aims to overcome these challenges to bring the humanoid robot into a human environment. We can think about what makes the problem more difficult. I think they are complex and nonlinear robotic systems, interaction with the environment or other agent, and multi-layered architecture. Since both robot models and constraints are usually nonlinear, we have many difficulties generating trajectories with a reasonable time specification. Also, the computation time affects the multi-layered structure instability. For this reason, I improved the performance of planning and control algorithms with a reduced computation time. Robust of the algorithm also very critical for operating the robot while interacting with the environment. So we propose more robust whole body control approaches in terms of unknown perturbations and uncertainties. I'm going to start by sharing my first study for efficient and direct trajectory generation of humanoid robots. This study aims to generate a trajectory to reach a final goal considering our full body dynamics and complicated constraint. We consider state input and contact constraint, and joint position, velocity, torque constraints are very practical one in real experiments. Also, we propose a very computationally efficient method without any simplification and reduced order model, like a linear inverted pendulum model. Here, I will briefly introduce the robot's full body dynamics and the state space model we used in this study. The rigid body dynamics of the underactuated robot is the first box of the equation. The floating-based robots, such as legged robot or humanoid robots, follow this underactuated robot dynamics. We can express the rigid body dynamic equation into the continuous time state space model, as you can see right side the box. In turn, we can discretize the state space model as shown in the last equation. Unfortunately, the final model is still nonlinear model. As you know, joint position, velocity, and torque constraints are linear fine. The contact geometry and kinematic constraints are nonlinear state equality constraint. More specifically, the contact position should be constant. Also, both contact velocity and acceleration must be zero. We consider contact wrenching constraint to prevent any slip and flipping motion of the contact body. This constraint is mixed state input constraint and even nonlinear because matrix W is a function of Q configuration. As you can see, we need to consider very complicated constraint to warranty the feasible behavior of the humanoid robot. Now we formulate an end-to-end trajectory generation problem for humanoid robot. More specifically, the problem is to find a feasible state and input trajectory to reach a final goal when the only initial state and desired goal output are given. Of course, complex constraints should be satisfied while generating the motions. This is really large-scale nonlinear optimal control problem, and it is very challenging to solve this problem for robot with a multiple contact. So we propose a novel method to solve this end-to-end trajectory generation problem very efficiently. Below figures intuitively show why we need to generate full state trajectory with a reachability analysis. The robot can reach the final goal output if the stated trajectory is dynamically feasible and reachable, of course, considering the contact constraint. Otherwise, the robot cannot reach the goal position and physical contact becomes unstable while follow the unfeasible trajectories. The main difficulty of this problem is that the robot is significantly high-dimensional system, and holonomic and non-holonomic constraints are mostly nonlinear. In this case, it is widely known Hamilton-Jacobi PDE-based reachability is almost impossible. Instead, we break down the end-to-end trajectory generation problem into tractable sub-problems as shown below figures. First, we obtain the sample-wise state reachable set using sampling-based technique. Then we formulate a POMDP problem to obtain an optimal sequence of output sub-regions. We check it is possible to move current output sub-region to the next one using our reachability tool. After checking it is reachable, we sequentially solve the standard optimal control problems to reach the final goal. Let's move on to the detail. First, we define the state sample-wise reachable set as a collection of the states satisfying all constraints we will have. This set is utilized to formulate next POMDP problem, of course. I briefly explain how to obtain the set. We draw a random state sample from a Gaussian distribution and update it to satisfy the state constraint using the gradient descent method and QP. In turn, we formulate the optimization to check there is at least one pair of control input and contact force satisfying our dynamics, input, and contact wrenching constraint. If there exists at least one pair, we can collect the sample in our reachable set. Based on the reachable set, we formulate a POMDP problem here. The main objectives of this POMDP problem is to obtain a sequence of output sub-region, of course, to maximize the reachable samples with conditional probability. To do that, we discretize the output space to make several output sub-regions. Then we create the output set using set mappings of the previously obtained reachable set. That set is mass scale Y in this slide. Then we define subset of mass scale Y associated with each sub-regions as shown in the figure A. Using the samples of the subsets, we formulate the observation and conditional probability. As described in figure A, if a state sample in output subregion Y can find another reachable samples in the next output subregion Y prime, we can consider the sample belongs to our observation. Using the cardinality of each set and observation, we can express the conditional probability Z. Secondly, we formulate a belief MDP problem using the previously obtained output samples and conditional probability. The reward function is formulated using the ratio of the cardinality of each subset. And the key is how to formulate the belief transition function here. We compute the covariance matrix of output samples in each output subregion. Then it's a principal singular vector to reflect the transition tendency as shown in figure B. The transition dynamics is computed using the principal singular vector and action vector as shown in figure C. The belief transition function can be formulated using the transition function and conditional probability Z. By solving this belief MDP problem, we can get the optimal sequence of the output subregions toward the final goal. To check whether the transition between the output subregions are feasible or not, we propagate our state by using the formulated QP. Of course, there exist two propagation methods here, full state propagation and boundary state propagation methods. The graph shows the comparison of the computation time of them. The full state propagation method is terminated by some memory issue on my laptop, but boundary state propagation method takes a linearly increasing computation time in terms of the propagation step. After that, we sequentially solve the optimal control problems. We formulate the standard optimal control problem to obtain feasible state input trajectories here. We define the performance index using output error and state error and some contact force term. And we minimize this performance index subject to discrete timed state space model, state inequality equality constraint, and input constraint, and contact range constraint. The desired output will be the final goal if the next subregion is the last one. Also, if the current subregion is the first one, then we will use the given initial configuration as the initial state of this optimal control problem. We can apply this trajectory generation approach to the legged robot and full body humanoid robot. This result is for the legged robot Draco P1. The pelvis of the legged robot succeed in reaching the goal position, of course, avoiding the obstacle like a table and chairs. The contact is maintained while moving the robot. Also, we analyze the computation time and compare it to the baseline approach. As you can see in the table, the proposed approach takes just 10% of computation time taken by a single very large NLP. We also verify our algorithm by using full-body humanoid robot Valkyrie. Valkyrie is also succeeding in reaching the final goal, as you can see in the right hand, of course, maintaining double support pace. These simulations show that our approach is very efficient enough to apply to the full-body humanoid robot, which is a very high-dimensional system. So far, I presented my first part of my studies, and the second study is reachability-based locomotion planning. We frequently use different models in layered structure of whole-body control. For example, we employed reduced order model at the planning level, but the feedback controller is based on the full body dynamics. We are interested in the discrepancy between planning and control models. In this study, we used the time to velocity reversal planner in the planning step. However, our whole body controller is a full state feedback controller. It means we don't know the planned result can be reproducible by a full body robot. Sometimes the planned position cannot be reachable due to the full body constraint. We propose a method to check the planned location is reachable. In turn, optimize the trajectory for the next whole body controllers. In our previous work, we planned the standard mass trajectory and full location using TBR planner. and generate swing foot trajectory using smooth interpolation like a B-spline or cubic spline. And trajectories of center of mass and foot are controlled by whole body controller, as shown in the upper flow chart. However, we propose an additional part of kinematic feasibility test, reachability analysis, and optimal control for better locomotion. By using the proposed trajectory generation process, we want to make sure safe and stable locomotion. Our TBR planner attempts to stabilize the robot by making its center of mass reverse direction every step. In its simplified model, the feet instantaneously change between swing and support mode, and the center of mass reversed its velocity at time t prime after the previous contact switch. The planner find and return the footstep location that caused the center of mass velocity to reach 0 t prime time after the foot switches. This planning method is very intuitive and easy to implement, also very fast and reactive, but full body constraints are ignored at the planning level. Let's take a look at the math. As I mentioned, the TVR planner utilizes a simplified model at IPM, so mathematical model is really simple. The planner only focuses on the center of mass behavior and full location. As you can see in the very first box, we can express the state space model as a linear system with a constant time duration t. Based on that linear system, we can determine the next foot location easily. Of course, to satisfy the apex velocity is at 0. But we still have many hand-tuned parameters based on our experiences, such as kappa in the last in the second box, and the apex velocity ts. Now we need to feedback controller to compute the control command to track the center of mass and foot position orientation trajectories. As shown, the shown block diagram is the whole body locomotion controller devised by Donghyun and I. I will explain the detailed framework in the following section later. What I want to say here is that this whole body controller cannot warranty whether the previous trajectories are feasible or not. So we propose a method for obtaining forward and backward reachable set. In terms of given contact mode, these methods are based on the sample-wise optimization and propagation. For computing the forward reachable set, we draw random control input sample, of course satisfying the input constraint, and solve the QP to obtain the joint acceleration satisfying all constraints. The initial state can be propagated forward in this way over some time horizon. Also, we can obtain the backward reachable set by drawing joint velocity samples. We project the joint velocity sample onto the null space of contact space for preventing any violation of contact kinematics constraint. Then check there is at least a pair of input and contact force in the formulated optimization problem. If yes, we can propagate the states backward, otherwise we discard the samples. By combining the previous forward reachable set and this backward reachable set, we can efficiently check the next contact location is feasible or not. Based on the previously computed reachable set, we can simply test our states are reachable or not over the context switching time horizon. Then we solve the formulated optimal control problem to generate a trajectory to change the contact mode efficiently. Of course, satisfying all the constraints. As a result, we can produce the optimized trajectory of the full body controller. If the next contact location is reachable, we will use this trajectory. Otherwise, we obtain another optimal trajectory to reach the closest location to the planned one. This can be achieved by adding additional relaxation variable epsilon in the bottom box. These are numerical simulation results. We employ the same TBR planner and same whole body controller. We assume a situation, the range of motion of hip joint is really limited to show the differences. Without the proposed method, the planner produces the diverging foot location, which is unstable. However, proposed method can make more stable walking due to the optimized trajectory. Also, this result can be applied to safe locomotion, avoiding some collision avoidance, and control limited locomotion with a very simple modification. The third study is about various whole body control approaches. Due to some time limitation, I briefly introduced this section. We have tried to improve the performance of whole body control method. I have collaborated with our alumni Donghyun to propose new whole body controllers. The first one is whole body dynamic controller. We combine a QP for computing contact reaction force and some projection-based method. I implemented some simulation work and analyzed the computation time in terms of the number of tasks. The computation time is between 0.5 millisecond, 1 millisecond, which is very fast enough for real-time implementations. The second whole body control approach is called the whole body locomotion controller. Whole body locomotion controller is updated with a 1.5 kilohertz, which is also very fast. We combine both kinematic level and dynamic level control. Using kinematic whole body control, we compute the desired joint position, velocity, and acceleration, of course, given the desired trajectories. In turn, we consider robust dynamics and contact force constraint in dynamic whole body control architecture. Based on this solution to the optimization problem, we obtain the torque command with the desired joint references. This video is a real experiment by Donghyun and I. Mercury walks stably, even though we throw the ball and push the torso. Next, I formulated the whole body control problems in many optimization forms and compared the solutions to each other. Given the current position, velocity, and desired acceleration, we can express the constraint rigid body dynamics as a linear. Humanoid robots are usually redundant systems, so the solution to whole body control problems generate different whole body behaviors in terms of their cost functions. Here, we formulate two optimization problems with different cost functions. The first formulation is to minimize the actuated torque, and the second one is to minimize the acceleration energy. Yeah, we can simply derive some analytic solution to each optimization problem as shown in the below boxes. There are some simulation results of previous two whole body control problems. We employ these controllers to track the central mass trajectory, and both control approaches follow the central mass trajectory very well. As shown in the right side figure, the error is almost zero. However, they produce different whole body behaviors. This study gives us a lesson that we should properly find the cost function by considering motion primitives and mission features of the robot. The next topic is robust whole body control or bipedal robots, of course, under some unknown disturbances. Draco 2 has very small feet and not that strong ankle actuations. So it is hard to keep the balance with a double foot pace under unknown disturbances. I have experienced that the ankle joint sometimes generates some oscillatory behavior and easily fall down when I push the torso of the robot. Therefore, we create more robust whole body control approach against this kind of external perturbations as an extension of our previous control studies. Without properly accounting for external forces, we found the robot may become unstable, so the desired task may not be achievable. In addition, the stability of joint aerodynamics has not been discussed yet when the external disturbances are applied to the robot. Instead, most of papers analyze the stability of the task aerodynamics. However, the stability verification based on task error dynamics cannot guarantee the full body stability of the robot. This is the detailed whole body locomotion controller when applying some unknown external forces. We are using joint space impedance control with a feed-forward torque command. Feed-forward torque command can be calculated by the optimization problem. By solving the optimization problem, we can decouple the closed loop joint space dynamics and make each joint space dynamics as a critical density system using a very classical PD control. Let's think about there is some unknown external disturbance with some contact force. Then we cannot decouple the joint space dynamics due to the force related to unknown part in the last equation. It means the closed loop joint space dynamics can be unstable by the external force. So we need to adapt our feedback gain to make our robot is stable. The upper figure shows the block diagram of our robust whole body control architecture. We utilize the whole body locomotion controller and predefine the task specification without further modification. What we need to do is to just adapt our feedback gain in whole body control architecture in real time. The lower figures show how to adapt the feedback gain of our whole body controller. First, we compute the ground reaction force by using whole body controllers. Second, the linear and angular momentums are computed by the centroidal dynamics. Using the centroidal momentum and ground reaction force, we can estimate the unknown external force with respect to a body frame defined a priori. Using the ground reaction force and estimated disturbances, we analyze the full body stability and adapt the gain to ensure that stability. The key feature is to employ both full body dynamics and centroidal dynamics. Because centroidal dynamics does not involve our control input term, so we can intuitively figure out the relationship between the ground reaction force and external disturbance without our controller. This is the detailed process to obtain the adaptive variable for our feedback gain. Using the rigid body dynamics and our whole body control formulation, we can express the joint acceleration for the actuated joint part. Unfortunately, we cannot express the joint acceleration formula as a second order differential equation due to the Ft in purple circle in right side. So our idea is to replace Ft terms with respect to Q dot and some constant term. Centroidal dynamics enable to approximate Ft without our torque command, as I mentioned. As a result of approximation, we can express some terms, including Ft, in terms of Q dot and some constant term, as shown in the last equation of the right side box. Using the previous calculus and approximations, we obtain the joint space error dynamics and formulate its state space model with a state, of course, the state consisting of joint position velocity errors. Now the state space model becomes linear. Furthermore, we can select some detailed variables to make omega hat is negligible. Then now it is very clear to show the stability of this system. V should be Hertz. In the characteristic equation box, we obtain second order equation with respect to eigenvalues. It means like a trace Kp minus Gp and trace Kd minus Gd should be positive when V is Hertz. From this condition, we can select proper adaptive variable epsilons, satisfying the condition given nominal natural frequency and damping ratio. We demonstrate a lot of simulations and experiments to validate our algorithm. Among these, I will show you 4 results as highlighted in orange color. We compare the result with and without our gain adaptation approach. First, we implement a behavior consisting of swinging in center on position with double support page. We generate a sinusoidal reference for the center mass, which is 0.03 amplitude and 0.5 frequency. The controller with a fixed gain falls due to the effect of external force. On the other hand, the adaptive gains prevent the robot from losing the balance. Secondly, we demonstrated real hardware experiment. Our robot Draco 2 is line-fit robot, so it is very challenging to keep the balance in double support page, of course, while pushing some torso. The scenarios are keep the balance under pushing and impact force in double support page. We verify that our adaptive gains, the robot becomes more robust in real experiment as well. Lastly, I compared the result with and without the proposed method in locomotion. We generated walking pattern using DCM planner and make the robot walking forward. We applied 100 Newton lateral force at the pelvis. The robot with a fixed gain falls due to the lateral force. In contrast, our gain adaptation method enables the robot keeps walking against the force. Without the modification of the controller, we make the robot more robust and stable against the external forces. This chapter is about hierarchical optimal covariance control. As I mentioned, whole body control is really good, but whole body control has also still a lot of issues and limitations. First, the whole body control relies on a classical PD control. It is well known PD control is not good for noisy feedback control systems. Also, we cannot consider the state covariance constraint in whole body controllers. For this reason, the terminal state may be very far from the desired goal state. So I employ optimal covariance control to solve this problem. The optimal covariance control problem is to steer the initial state drawn by a Gaussian distribution to a specific desired terminal Gaussian distribution, as shown in the right side figure. However, most recent covariance work focuses on a single stochastic system, not hierarchical system. So I want to extend this optimal covariance control approach to hierarchical task space systems. Let's compare the proposed hierarchical covariance control with a hierarchical QP. Hierarchical QP solves only a single time step least square error minimization problem, of course, with a deterministic model without any uncertainty. However, hierarchical covariance control considers a stochastic system with a multiple time horizon. Both approaches aim to control multiple hierarchical tasks. In this sense, I think hierarchical covariance control is one of the extension of our whole body control for stochastic systems. The punchline of the proposed approach is quite simple. First, we transform the rigid body dynamics model to multiple stochastic systems considering noise process in the task space. In turn, we linearize and discretize the stochastic system. Then we solved a lexicographical optimization problem for all given tasks. We benchmark a hierarchical QP structure to control multiple hierarchical tasks of the robot in this way. We define the task space covariance control problem in problem 1. We assume we know mean and covariance of the initial and final stage a priori. The performance index consists of expectation of quadratic terms of state and input. And we consider 5 constraints: state space model, terminal state mean constraint, terminal state covariance constraint, chance constraint using Euclidean distance, and constraint for task hierarchy. The last constraint can be replaced to the null space projected task space Jacobian, task space dynamics. It means the B matrix in constraint 1A contains the null space projection matrix. Unfortunately, we need to employ NLP to directly solve the defined problem. However, we want to solve this problem using convex optimization because convex optimization is much faster than NLP. To do that, we define a new decision variable to formulate our problem as a convex optimization problem. We consider state space model concatenated for all time horizon and control input U. In this case, Mescal K is the original decision variable. The closed loop system can be expressed in the second box with a decision variable K. However, we don't want to consider the inverse of our decision variable K. So we represent the state of the closed loop system with a well-defined decision variable psi. Using this new decision variable psi, we can rearrange the performance index and all constraints to be convex. First, the performance index consists of two Frobenius nodes, which is convex. Then the terminal state mean constraint 1b becomes linear in terms of our decision variable psi. The terminal state of covariance constraint 1c and the chance constraint 1d are formulated as positive semi-definite matrix constraint. I will skip the detailed derivation of this due to the time limitation. Please see the detailed derivation in my thesis. Now we formulate our problem 1 as convex optimization problem, which can be solved using semi-definite programming. Good news is the SDP is much faster than NLP, and we can obtain the final control input by sequentially solving the formulated covariance control problem for all tasks from the first one to the last one. This is a simple numerical simulation. We try to control double pendulum on a card. The higher prioritized task is to control the end effector position, and the lower prioritized task is to control the card position. The simulation results are shown in figure 1 and 2. And we compare the result with operational space control. The operational space control and hierarchy covariance control are represented in orange color and blue color, respectively, in the graph. With the same level of uncertainty, the proposed hierarchical covariance control results in much less L2 norm error and terminal state covariance, of course, compared with the result of operational space controller. The last study is hierarchical model predictive control. The current whole body control method has many strong points. The existing methods are very, very intuitive and employing full body dynamics and constraint. And we can compute the whole body control approach very fast. And we can use them for real-time application. However, they still have shortcomings, as I mentioned. The method considers a single time step optimization problem. So it may generate very myopic behavior and depends on the predefined hand-tuned trajectory. Also, we cannot guarantee the optimality over the entire time horizon. On the other hand, optimal control and MPC can consider multiple time horizon, of course, to guarantee the more global optimality. In addition, we don't need to reference trajectories in many cases. We can solve optimal control problem without nominal trajectories. However, it takes very long time to solve, and especially for the larger scale system, like a humanoid robot or some constraint manipulators. Let's take a look at the proposed approach using MPC. We express the state space model of underactuated robot, and the state space model is nonlinear. Yeah, unfortunately. We can formulate a standard optimal control problem. One special part of this optimal control problem is that we borrow some physical intuition of whole body controller. We will minimize the performance index subject to the state space model, inequality constraint, and equality constraint. Unfortunately, this problem is nonlinear optimal control problem. Almost every part of this problem is nonlinear and non-convex. In addition, another challenge is to formulate the constraint for task hierarchy for multi-time step. The main idea is to formulate the constraint for task hierarchy using some tracking error of each task. Also, we will convert this nonlinear optimal control problem to quadratically constrained quadratic program called QCQP. First, we linearize the state space model. There are a lot of linearization techniques. Among them, we select a simple way to linearize the system along nominal trajectories. Given nominal trajectories of the state and input, we linearize the state space model. In turn, we discretize it with discrete time interval delta tau. Then, we define two decision variables, which are vertically concatenated all states and input variables over time horizon. We can obtain linear equality constraint with our new decision variable Mescal and Mescal X and Mescal U. Secondly, we define the constraint. We define the constraint of task hierarchy. Given n task, the tracking error of higher prioritized tasks should be less than those of lower prioritized tasks. We define this constraint using the square of two norms of the task tracking errors. These inequality constraints are nonlinear because the task function is usually nonlinear. Thus, we convexify this inequality constraint using nominal trajectory as left side inequality constraint. We properly stack the Jacobian and coefficient vectors for all time steps. Then the inequality constraint can be expressed as quadratic inequality constraint in terms of our decision variable Mescal X. The third part is to convexify the performance index. We want to express the performance index using the quadratic and linear terms of the decision variables. Before convexifying the performance index, we extend the expression of running and terminal cost functions. We replace the Jacobian J and vector B with the stack of Jacobian, gain, and desired task velocity vectors for all multiple tasks. Then the lambda matrix and B matrix B vector can be recalculated using the stacked matrix and vectors. Then running cost and terminal cost are expressed using quadratic and linear term of the state and input variable as shown in the upper body. In the previous slide, we linearized and convexified the nonlinear terms to formulate our problem as a convex optimization problem. Now, the optimal control problem becomes a QCQP. We can solve this problem using convex optimization tool much faster than NLP. With proper prediction and execution time horizon, we iteratively solve this QCQP and update our dynamics of robot like described in algorithm 1. We verify the proposed approach using numerical simulations using a manipulator Scorpio. In this simulation, we define two hierarchical tasks. The higher prioritized task is to control X, Y wrist position, and the other task is to control Y and Z elbow position. The existing whole body control approach minimizes the higher prioritized task first and handle the lower prioritized task, as shown figures in the first row. Compared with whole body control, the proposed NPC method slightly increases the tracking error of a wrist positioning task, but the secondary task error is significantly reduced, as shown in the red lines of the second column figures. In detail, we can compare the tracking errors here. Compared with whole body control, the proposed NPC approach increased about 0.02 meter error of the wrist positioning task, as shown in the first figure. On the other hand, we significantly reduce the tracking error of the elbow positioning task, approximately 0.1 meter, as shown in the second figure. Our last figure shows that the wrist position tracking error is always smaller than that of the elbow positioning. Also, the proposed approach results in smaller accumulated task tracking error than whole body controller. The proposed NPC method reduces the sum of tracking errors. with warranting the wrist positioning task error is always less than the elbow positioning task error. In addition, we formulate this optimal control problem as a convex optimization. For sure, this convex optimization is much faster than nonlinear programming. This is conclusion. I have these 5 journal papers and another 5 conference papers. In addition, I collaborated our lab mates to produce 3 e-papers, and I will have 2 more papers in near future. I will briefly summarize the contributions here, really briefly. In chapter 2 and 3, we propose a new trajectory generation and optimization approach for multi-contact robots. We improve the computational efficiency of the algorithm, and we provide new, very efficient, computationally efficient reachability analysis. In chapter 4 and 5, we show some contributions on robust whole body controllers, make our robot becomes more robust in terms of unknown disturbances. In chapter 6, we propose a new algorithm called the hierarchical covariance control and formulate the problem as convex optimization, which can be solvable very fast. And chapter 7 shows the advancement of MPC to execute multiple hierarchical tasks. I have several open questions and future work here. Most algorithms in my thesis rely on optimization technique. So computation time is really matter for real hardware demonstration. So we need to improve the computation efficiency. Also, I assume our model is accurate, but in reality, the models are frequently inaccurate. So I need to improve the model accuracy using some learning techniques. Lastly, I need a very interactive high-level planner for additional safety warranty. Also, there are too many hyperparameters needed to be tuned for our optimizations. If we find these parameters very autonomously, our approach will be more useful in real human life. Yeah, this is the end of my presentation. Thank you very much.